Good day. Welcome to the second video on Chapter 1. In this video, we will be doing Chapter 1.2, discussing the dot product and norm. So we just started our vector journey. There's so much more to know and do. Alright, so let's start with a definition. So if x and y are two n-dimensional vectors, we define the following idea. It's called the dot product. Some textbooks call it the scalar product. And it's defined as the following real number. So x dot y, that dot is very important in the notation. We take the corresponding components, we multiply them, and we add them. So x dot y is going to be multiply the first components, plus multiply the second components, plus etc. up until the last, the nth component. Alright? You can write this in fancy summation notation as the sum I going from 1 to n of xi times yi. Remember, xi is the ith component of vector x, and yi is the ith component of vector y. Alright? So the dot product spits out a real number. So it turns an nd vector and another nd vector into a real number. Alright? So guys, it's good to make your own examples, or do all of the examples and the exercises in the textbook. Alright? So, here's an example. Find the dot product x dot y and y dot x if x is this 3D vector and y is this 3D vector. Alright, so let's do the mathematics. So x dot y, we want to see the calculation. So the first component of x is 2, the second component of y is minus 2. Then the second component of x is 3, and the second component of y is 4. And then the last component of x is 9. We multiply it with 1. So what is this? This is minus 4 plus 12 plus 9. So minus 4 plus 12 plus 9, that is minus 4 plus 12 is 8. 8 plus 9, that works out to be 17. Alright? So x was a 3D vector, y was a 3D vector, but x dot y evaluated to the number 17. Now let's do y dot x. Alright, so by definition, it's the first component of y times the first component of x plus the second component of y times the second component of x plus the last component of y, times the last component of x, which is 9. So this works out to be minus 4 plus 12 plus 9, which also evaluates to be 17. Quite suspicious. Alrighty, now let's do another example. Let x be the 3D vector 239 and z be the 4D vector 2514. And the question is find x dot z. Alright. Now you can immediately make the following observation. Note that x is an element of R3 and z is an element of R4. So x dot z is undefined. So you got to know your definitions quite well, and the dot product only works if the vectors are coming from the same dimension. So because x is 3-dimensional and z is 4-dimensional, it's nonsensical to talk about x dot z. Alright? So you can only do the dot product if the vectors are from the same dimensions. Alright? So quite easy. So now we know what dot product is. So the next thing is we want to know some properties of dot product. Alright? And the important ones are captured in theorem 1.2.3. So let x, y, and z be algebraic vectors in Rn. So they're unknown n-dimensional vectors. And alpha and beta are real numbers. So we have the following properties. The first one is called positive definiteness. So that x dot x is greater or equal to 0. So if you take two vectors and you dot them, the dot product can be positive, negative, or 0. But if you take a vector and you dot it with itself, then it's either naught or positive, and hence why it's called the positive definiteness. Alright, so x dot x is either naught or positive. But we can even say more. X dot x is 0 if and only if x is the 0 vector. So what it means is that part A happens if and only if part B happens. So part A implies part B and part B implies part A. So if you have to prove the if and only if part, you're going to have two paragraphs. You're going to assume A, deduce B, and then in a new paragraph, you're going to assume B and deduce A. All right, so please give it a go. All right. We saw in our specific example that x dot y is the same as y dot x. This is always true, and this is known as commutativity. All right. And another nice property of the dot product is the following: that x dot alpha y plus beta z, that is equal to alpha, the scalar x dot y plus beta x dot z. All right. So here we only have one dot product on the left hand side, and on the right hand side we have two dot products, and they are always equal, and you can prove this, so please do it. So for the video, I am just going to take the case where x and y are 2D vectors, and I'm going to prove that x dot y is always equal to y dot x. So no matter what 2D vector x is, no matter what 2D vector y is, this is always true. All right? So remember, we like to prove things so that we know it's true, so we can use it in solving other problems. All right? So let's start again by having a handle on the component. So let vector x be x1, x2, where x1 and x2 are the components and are real numbers. Let vector y have components y1 and y2, where y1 and y2 are real numbers. All right? So you know, depending what you want to do with vectors, most of the time it's nice to know what the components are. So hence we have this little paragraph. So we want to prove this identity. So we're going to start off by saying the left hand side is equal to x dot y. Now x is the vector x1, x2, and y is the vector y1, y2. Notice the dot here, guys, and notice the dot here. All right? And then if I use the definition of dot product, then I know it is going to be the first component of vector x multiplied by the first component of vector y plus the second component of vector x multiplied by the second component of vector y. All right? And now we're going to use a fact from high school that if p and q are real numbers, then p times q is the same as q times p. So applying this fact here, that term is the same as this term. Applying the fact, we know that x2 times y2 is y2 times x2. All right? So here we use the fact that multiplication of real numbers is commutative. All right. And now, if you look at this, we can interpret this as a dot product. We can interpret this as this vector dotted with this vector. Why? Because this is just the definition of dot product. All right? So, this dotted with that is equal to that expression. And now, if you look at this, it has a name. It's called y. Dot, this has got a name. It's x. And that is equal to the right-hand side. And we're done. All right? So, in this proof, we didn't know what x was. We didn't know what y was. And also, in our proof, we explained clearly why we move from the one line to the next line. All right? What other properties or other definitions we are using. All right? So again, please practice being good with proofs and do tackle the other proofs as well. All right? So we now know that these properties of dot products are true because I've proven one and you will prove the rest. Alrighty. Now please do example 1.2.4. I'm not going to do it in this video, so I'm leaving it for you to give it a go. All right? But now I want to talk about the other idea, which is the norm. All right? So the norm, we will see geometric meaning later in this chapter. But for now, we say the norm of algebraic vector x with components x1, x2 all the way up until xn, so it's an n-dimensional vector, is a real number, and it's going to be defined as follows. The norm of vector x, notice the notation. All right? So it is two vertical lines, vector x, notice the line on top of vector x, and then two vertical lines. That's equal to the square root of x dot x, which is equal to, if you apply the definition of dot product, it's the square root of x1 squared plus x2 squared all the way up until xn squared. So you take each component, you square it, you add them all up. Once you've done that, you take the square root of that. All right. Now, Remember, if you take a square root, you've got to worry about taking a square root of negative numbers, all right? But we know by theorem 1.2.3, part 1, the positive definiteness, that if you take a vector and you dot it with itself, it's greater or equal to 0. So the square root of x dot x always exists. And so this definition is well defined. Nothing bad can happen, all right? Now, more definitions. Now, if x is an n-dimensional vector, we say that it is a unit vector if and only if the norm of x is equal to 1. All right? Guys, this is very important. If you have a vector and its norm is 1, it's called a unit vector. If it's a unit vector, the norm is 1. So do unit vectors exist? And the answer is yes. Here's 3 examples in R3. There are actually infinitely many in R3, but if you take the vector 1, 0, 0, it's called vector I. Notice the line on top of I. It's a unit vector. I'm going to leave it for you to work out the norm and see it's equal to 1. J is the vector 0, 1, 0. It's a 3D vector. If you work out its norm, it's 1, so it's a unit vector. Vector K is the vector 0, 0, 1, which is, again, a 3D vector. And if you work out its norm, it's equal to 1. All right, so I, J, K, very important. They are known as unit vectors in R3. All right. Now, I, J, K is also very special. All right. The set containing I, J, K is called the standard basis of R3. And you might ask why. All right. So here is a reason why. So if you take vector x, and as always, we use convention with components x1, x2, x3. So if x is a 3D vector, it has 3 components. And we give them names, x1, x2, x3. Now, we know by vector addition, this we can rewrite as this vector plus this vector plus this vector. All right, so because of the way vector addition works. And now because of the way multiplying a vector with a scalar, I can rewrite this vector as x1 times the vector 1, 0, 0. I can rewrite this vector as x2 times the vector 0, 1, 0. And I can rewrite this vector as x3 times the vector 0, 0, 1. And now, from above, we know that this vector is called I, this vector is called J, and this vector is called K. So we see that vector x is some scalar multiple of vector I plus some scalar multiple of vector j plus some scalar multiple of vector k. All right. So essentially, any vector is a linear combination of vectors I, j, k. All right. And so you see that 3D vector is this 3D vector plus this 3D vector plus this 3D vector. All right. Now, obviously, you can see x1i plus x2j plus x3k. That's quite a lot to write. And again, notice the notation. x1, x2, x3 are scalars, so no lines on top of them. I, j, k are vectors, and hence we're putting lines on top of them. All right. So that is just a little explanation of what any vector x can be. It can be written in terms of a linear combination of vectors I, j, k, and a vector in general has a norm which isn't 1. But I, j, k is these special vectors, and they have norm 1. And if it have norm 1, they are called unit vectors. All right. Now for a big theorem. It is named after 2 mathematicians. It's called the Kaushischwarz Inequality. So please Google who was Cauchy and who was Schwarz. All right. Now the theorem says the following: if x and y are any n-dimensional vectors, then the absolute value of x dot y. So the way you should interpret the left-hand side is the absolute value of x dot y. So remember, if x and y are vectors, the dot product is a number, and we take the absolute value of x dot y. That is always less or equal to the norm of x times the norm of y. All right, guys? This is a huge result for this chapter. All right? So you must know the proof for semester test 1. So I'm not going to do it in this video. So please read pages 10 and 11. All right? write it out several times, and if you think you know it, please explain it to a classmate, all right? But as you know, logic is important in mathematics. So what can we draw from the Kaushischwarz inequality, all right? So one of the things that we can conclude is that the absolute value of x dot y bigger than the norm of x times the norm of y is always false, all right? So that's one of the things that we can conclude from this theorem, all right? That the absolute value of x dot y can never be more than the norm of x times the norm of y. You can try as hard as you may, all right? This will never, ever, ever happen, all right? And again, theorems are important because we can conclude things and we can use it to solve new problems, all right? Now, what we can also conclude from this result is that one of two things can happen. If you calculate the absolute value of x dot y and you calculate the norm of x times the norm of y, one of two things can happen. Either that the left-hand side is less than the right-hand side, or that the left-hand side equals the right-hand side, all right? So this is obvious because we know that this symbol means either equal or less than equal, all right? So because of the meaning of the less than equal symbol, it means that either the left-hand side is less than the right-hand side, or that the left-hand side is equal to the right-hand side. Let me quickly fix this up. So that means either it's less than or equal, all right? So that is what it means, all right? Now, a good question to ask, and if you're doing mathematics, if you're doing science, you've got to ask questions. And here's a very good question to ask. When is the absolute value of x dot y equal to the norm of x times the norm of y? All right? So if you're curious, and you've got to be curious if you're doing mathematics, so please ask your own questions. Ask your friends. All right? Now, the answer to this question is that this happens if and only if y is a scalar multiple of x, or x is a scalar multiple of y for some scalar alpha, which is a real number, all right? So it means the following, that if the absolute value of x dot y is the same as the norm of x times the norm of y, then it implies either y is alpha x or x is alpha y. One of the two happens for some scalar alpha. And this is an if and only if. Guys, again, notice the if and only if. So this result even goes the other way. So if y turns out to be a scalar multiple of x, or x is a scalar multiple of y, then it implies that the absolute value of x dot y is the same as the absolute value of x times the absolute value of y. I'm not doing it in this video, so that little fun proof or exercise I'm leaving for you to do, all right? You've got to get your hands dirty doing mathematics, all right? So please find yourself pen and paper and do exercise 1.2 number 6 to see why this is so. All right, this is an if and only if. So you're going to have two parts to do. You assume the first part and you deduce the last part, and you also in a new paragraph assume the last part and you deduce the first part. All right, so an if and only if means two jobs to do. All right, so please do it. All right. All right, so more properties about the norm, and here we're going to prove the following, or mention and just prove one of them. So if x and y are two algebraic n-dimensional vectors and alpha is any real number, then the following holds. Number one, that the norm of x is greater or equal to 0, and we can even say more than that, that the norm of a vector is 0 if and only if x is a 0 vector, and vice versa. The 0 vector is the only vector whose norm is 0. All right. Number 2 is quite interesting, and please give it a go. That the norm of alpha x is the absolute value of alpha times the norm of x. All right. And number 3, the triangle inequality. That the norm of x plus y is less or equal to the norm of x plus the norm of y. And to do number 3, you get to use the Kaushischwarz inequality. And this is the reason why the Kaushischwarz inequality is so important. Because after you've proven the Kaushischwarz inequality, you can prove number 3, that the norm of x plus y is less or equal to the norm of x plus the norm of y. Again, I don't want to deprive you from this beautiful exercise to do, so you got to do it. But I'm going to prove number 1. all right, which is if x is a real, if x is a 3D vector, then y is number 1 true, all right? So let's dissect number 1. So number 1, we actually have a lot of things to do. So we've got to do this. This is our first job. So let's look at the norm of x. Now, again, we're going to make our lives easy and say let x be a vector with components x1, x2, x3, where x1, x2, x3 are real numbers, all right? So then the norm of x, by definition, that is the square root of x1 squared plus x2 squared plus x3 squared, all right? And now we know that x1 squared is greater or equal to 0. We know that x2 squared is greater or equal to 0. So we know that x3 squared is greater or equal to 0. So x1 squared plus x2 squared plus x3 squared is greater or equal to 0. And so thus the square root of x1 squared plus x2 squared plus x3 squared is greater or equal to 0. So the norm of x is greater or equal to 0. All right, so we've done the first part. That the norm of any 3D vector is not or positive. All right. Now, the second part is an if and only if part. All right. It's an if and only if part. So we got to prove that the first part implies the second part. And we also got to prove that the last part implies the first part. All right. So let's start that part as number 2 and let's call that job 3. All right. So let's start off by saying if x is a 0 vector, then x is the vector with component 0, 0, 0 because we're only doing the 3D case now. So the norm of x would be the square root of 0 squared plus 0 squared plus 0 squared, which is the square root of 0 plus 0 plus 0, which is 0, so true. All right. So let's take stock. We've done number 1, happy. And we've proven that if x is the 0 vector, then the norm of x is 0. Then we've done that part. And now we've got to do this part. All right, so let's assume the part. Notice I'm starting this by saying if the norm of x is a 0 vector, then the norm of x, it's the square root of x1 squared plus x2 squared plus x3 squared. That's equal to 0. So if we square it, we get that x1 squared plus x2 squared plus x3 squared is equal to 0. All right? We can see that if x1 is not 0, then x1 squared will be positive. And so let's call this a 1. So 1 is not true. So x1 must be 0. All right. Likewise, if x2 is non-zero, then x2 squared is greater than 0. So 1 is not true. So x2 must be 0. Likewise, if x3 is non-zero, then x3 squared would be positive. So 1 is again not true. So x3 is equal to 0. So thus, x1, x2, x3, which is vector x, will be the vector where all of the components are 0. So it's the 0 vector. And so x is the 0 vector, which is what we wanted to prove. All right. I hope you enjoyed this video on norms and dot product. The next video will be on chapter 1.3. Have a lovely day.